What I like about these propositions is that now I can actually understand the definition at the beginning of the angle in a segment. It actually doesn't really, it's one of those proposition definitions. That's how we do it now, right? Where you prove something and then as a result a certain definition is kind of sensible. But okay, I think we're up to proposition 21, isn't that right?
Yeah, that sounds about right.
Yeah, so that's me. Alright, here goes. So this basically says that the notion of the angle in a segment is a well-defined thing. I'll define segment because I believe we skipped over discussing that. In a circle, the angles in the same segment are equal. Okay, so what's a segment? Oops. Billy says every time he watches the recording, he feels very pained by our insufficiency in drawing circles and wants to add a circle tool to reduce his suffering. And I say, no, our circles are awesome. We don't need a tool.
Sometimes we need wonky circles, right?
That's right, exactly. Sometimes we need wonky circles. So there, Billy. Okay, so a segment of a circle is between a line, in this case BD, and the circumference. So this is a segment. So I'm going to go ahead and connect BD. So let ABCD be a circle. As usual, A and E will appear later. In fact, yes, C is just one of these random points. Okay, so proof. Let A, B, C, D be a circle. I think, yeah, he calls the segment BAED. BAED, a segment. Notationally, that's exactly the same as a circle, right? Just naming 4 points on it, but you understand what I mean from what I said earlier. Okay, so that's a segment. So to take two angles in a segment, so that means two angles on the same sort of part of the circumference, namely BD, right? So pick 2 points, A and E, and then we're going to connect them. And the two angles we're talking about not really suggested that it's passing through the center. It's a bit unfortunate. Let me move A just a second. That'll do. So the two angles I'm going to prove are equal are BAD and BED, only to be surpassed by proving MAD is equal to LAD in book 6. So bad is equal to bed is what we have to prove. So let F be the center. And join FB and FD. Then, by what we did last time, BFD equals twice BAD, and also at the same time twice BED. So BAD and BED are equal. We've discussed this sort of halving things. The halves of equal things are equal at some point a year ago or something. The point being that if they weren't, then you could derive a contradiction by adding them to themselves and getting something different. Okay, so that's it. And
yeah, I don't remember if this is how we proved it when I was a child. But,
yes. Yeah. So
of course, when we learned this when we were young, it's not like we did it in a monolith, right? We just got told these things, and I can't remember which one came first, right?
That's right. Yeah.
Yeah.
Okay. So the conclusion from this is that the notion of the angle in a segment is well defined, right? Because it's independent of which point A you take in the segment. Okay,
Cool.
your turn.
Right. So detach, attach. All right. So the next one is also pretty short. This one is one that we know from school probably. So let me just clean up some of this. I might have to take my jacket off. Euclid. Oh, this is proposition. What am I doing? Proposition, book 3, 22. So this is about quadrilaterals inscribed in a circle. So for quadrilaterals, oh, it's raining.
It's not supposed to happen if someone's attached to speaker. Oh well.
Is that right? I'm attached, right?
Yeah, you are. That's a bug.
All right. That's a fun bug.
It'll stop shortly, I imagine.
Cool. So we've got a quadrilateral within a circle. I guess this means all the vertices are on the circumference. It's not just any old quadrilateral inside the circle. The sum of the opposite angles is equal to 2 right angles. 2 opposite angles is equal to 2 right angles. So we had a proposition earlier talking about the angle sum of a triangle being equal to 2 right angles. So we're going to use that somehow to prove this. So we're going to, let's draw a circle. My circle's always blue. I don't know why. So we've got the quadrilateral. We're just going to draw some quadrilateral here with the vertices on the circumference, on the circle. I guess the same thing. And we can call the circle ABCD in this case, right? Because we've got the 4 vertices. Okay, so that's a quadrilateral. And of course, we're going to join the opposite angles. I guess in geometry, we often just join all the lines, join all the points with lines, and see what we get. So we're going to prove this, and hopefully the proof fits within this board. So we're going to first invoke proposition 321. And that says the angle BAC and BDC are equal. Let me just mark them. BAC. All right, so this one, and then BDC are equal. Why are they equal? Well, we just proved that angles on the same segment are equal, right? So these are on a segment. I guess the segment is BADC, right? So the segment is this segment here, all right, starting here and ending there. And so they're equal, so I've marked them. Let me just go back and write this down. So the angles now BAC and BDC are equal. Okay, so I'm just going to write they're in the same segment. In the same segment. Okay, and similarly, we're going to say that two other angles are equal, I'm just going to write this shorthand. BCA is equal to BDA. Again, I mark them on here. BCA is equal to BDA. This one here, right? So we've got. So now you can see, what's going on. We're going to invoke the angle sum of a triangle as being equal to two right angles, and that will tell us that ADC, which is the one you can see on the diagram, is the sum of the green and the red, is plus ABC add up to two right angles. So that will be it. So by proposition, so this is an earlier one from book 1, which tells us the angle sum of a triangle is equal to two right angles. The angles, the three angles of ABC of the triangle ABC is equal to two right angles. Okay, hence I'm just going to finish it. ADC plus ABC is equal to two right angles. Just fits. And that's it, right?
Yep. Cool.
Back to you, Dan.
Yep.
Let me just recap.
Okay. 23. So this one's pretty cool. The written form is a bit hard to pass, but on the same straight line, they cannot be constructed two similar and unequal segments. What does similar mean? What does equal mean? Well, it's a good question. As usual, you just read the proof on the same side. Okay, so, well, suppose for a contradiction, we can construct, so we'll put a line, AB, two similar and unequal segments. So remember, a segment is the part of a circle sort of cut off by a line, where you take the part of the circumference on one side of a line. So what does it mean for two segments? Well, so remember that once we have, so here are the two segments of two different circles. What does it mean for them to be similar? Well, remember, once we have a segment, we have a well-defined angle of the segment. So to say they're similar is just to say those angles are equal. That's actually definition 3.11 says similar. So two segments are similar means same angle. Right, that's all. Okay, so for them to be equal, on the other hand, is just to say that, yeah, this is actually tricky, I think. For them to be equal, well, it's the intuitive meaning, which is that on the board they coincide, right? Now, there are many forms of equality in Euclid, Sometimes it means literally figures that coincide. Sometimes it means they have the same area, etc., or could be displaced into one another. In this case, what we mean by equal is literally that those two curves from A to B are the same curve. And the way it plays a role in the proof is as follows. I'll come back to the commentary after we've gone through the proof. Suppose they're similar, that is the same angle, and unequal, that is sort of like in scare quotes for the moment. But so just take two segments which are similar. Forget about equality or not. Just take two of them. Pick a point C. Now, how do we know that one segment lies entirely inside another segment? Yeah, actually I hadn't thought about that. Doesn't matter as long as, so I need to pick a point C that's on one of the segments and interior to the other segment. If that's impossible, then for this segment, then it lies entirely outside the other one. Then pick the other one. So I guess, we'd have to invoke some of these basic propositions about lines to make sure there wasn't some, like we'd have to rule out the configuration where the segments like don't lie at all inside each other and don't intersect or something like that. But that seems like it should be pretty easy. Okay, anyway, so we pick a point C on the interior segment, and then I'm going to draw a line, which we know has to hit the outside segment, or I don't need them to be entirely contained in one another, as I said. So hits the other segment, and then connect this line. Now, the sense of equality I need is that D is different to C. Sorry, the sense of inequality that I need. So just taking the negation of that, two segments are equal if this can't be done, right? So any line that you draw through a point on one of the segments, that is also a point on the other segment. So that's a kind of way of detecting that two curves coincide, I guess, right? At least this particular kind of curve. Anyway, so that's enough fussiness. So now we've got two triangles because I can connect C to B. So I'll just connect. So pick C, connect AC, CB, DB, where D lies on AC. Okay, now we're basically done. Since the segments are similar, ADB equals ACB, but that's impossible because one is an exterior angle.
You're right.
This is impossible because if you think about this triangle in here, because BCA is an exterior angle to the triangle BCD, which is greater than the interior angle BDC by proposition 1.6, I think, 16, sorry. Okay. So that's kind of more complicated than it looks in terms of just getting your head around the definitions, but the principle. It's quite interesting that we see like Euclid pushing in the direction of infinitesimals, and now like a couple of propositions later pushing in the direction of like thinking about general curves or something, segments of circles. Yeah, Did we want to stop there, or did you want to do?
We can do one more. I think
Yeah.
the next one is uses this proposition that we just did over here. So
Right.
yeah, let's do one more. I think we can finish it.
Great.
Okay, let me just check. Okay, so yeah, these propositions all kind of depend on each other, and they lead to more and more results. So it's nice to kind of do them in a row and see how they apply, right? So this one is well, thanks Dan for explaining similar. When I was reading this, I didn't read through 23 carefully, so I was like, what a similar segment. I guess I just assumed that they were like, equal in length,
Right. Yeah.
which I and then I was like, why don't they just call it equals? Well, but I guess I understand now, so that's good. So similar segments of the same circle. That's right. Guess we're only talking about one circle here, on equal straight lines that equal. Yeah, so like I guess the way I was thinking about it, that didn't make too much sense because if they were equal, why are we proving that they're equal, right? And so I guess the picture goes like this. Okay, so we've got segments, right? Let's just call them A and B, and then another one which is C and D, right? And I guess the straight lines we're talking about are going to be these lines. Right. So a priori, we're not saying that the arc AB, right, is the same as the arc CD. We're just saying that this line, didn't use the right tool there. This line, AB is equal to CD. Okay. So the claim is that the similar segments, so the angle on the circumference with endpoints on this segment are the same, but in fact, if this is the case, if these lines A, B, and CD are the same, the segments are actually equal to each other. And I guess equal is the kind of the strong form of equality, that they actually are the same when you kind of move one to the other. You can like apply one figure to the other, and it's exactly the same figure. And that's exactly what we're going to do in the proof. We're going to apply one of the figures to the other. We haven't done this in a while, but this is a neat trick, right? So Euclid uses this a lot. So apply the segment. So I guess I'm just going to call it AB. I'll mark it in the diagram. So the segment AB is this one. The segment CD is this one, and I'm just going to call it AB with a little arc on the top, so that we know what we're talking about. I'd like to use fewer letters if possible. AB to CD, right? And so we're just gonna like move A to the point C and then move B to the point D. Well, because the lines are equal in length, AB is actually gonna be exactly CD when we apply the figures, right? So with A coinciding with C, and since AB is equal to CD, these are the lines A, B, C, D, right? The point B will coincide with D. All right, so we moved them on top of each other, and now I'm going to go to the next board and draw some more pictures.
You're drawing them on segments of one circle, but that's actually not implied, right? Can you?
Oh yeah, maybe this is. Yeah, maybe you're right. Maybe I shouldn't say that they're on the same circle. So they're just segments on.
Yeah, let's just disconnect these.
Yeah. Let's just disconnect them. Okay, so yeah, because otherwise it's kind of, maybe there's less to prove there, right? Okay, let's go over here. Okay, let's check. Okay, so let's erase. Okay, so there are three possibilities. I'm going to just draw these possibilities here, right? So this is the line, the right tool, the line. This is like AB or CD, right? Right. So this is now equal to C. This is now equal to D. So one of the possibilities is that you've got it like this. This is the arc AB, and then the other one is completely on the other side, right? This is CD, right? So right. So I guess this is them not intersecting. The other possibility is the other way around, right? I actually just put it here. It's easier to just draw it like this, just flipped, right? So CD is here. So there's a CD and then AB is on the outside, right? And the third possibility is erase. So the third possibility, I got the wrong color here. The third possibility is, well, I mean, this is not necessarily, the case. Like it intersects somewhere, and possibly elsewhere, right? So I'm not going to draw the rest of it, but there is a point of intersection, right? Okay, so where's our contradiction if A, B, and C, D aren't the same? Well, in cases 1 and 2, right? In cases 1 and 2, right? This contradicts proposition, the last one.
Yeah.
Yeah, maybe I'll just, sorry, I've got some pop-ups here to get rid of. So cases 1 and 2 contradict proposition 3, 23, I guess that was the last one, right? We just proved this, and so I won't belabor the point. And the third case, case 3 contradicts 320. So why is that? Did I get the number correct?
That's the angle at the center is double the angle at the circumference. Is that really what you mean?
I think I probably copied down the wrong
number. No, you mean 10.
10, right.
Yeah, 10 says two circles can't cut each other at more than 2 points. Yeah.
More than 2 points, right? So since circles, yeah, that's right, cannot meet in more than 2 points. Greater than 2 points. So where are the more than 2 points? Well, there's one here, and then there's one here. Right, so that's not good. So so they can't intersect, they can't contain each other. So then, I guess the only possibility left is that they're exactly the same. I didn't think through this completely. Is that?
Well, I feel like this is basically. I mean, I don't see how this is really too different from 23. Like,
right.
I had to actually consider this case 3, didn't I?
Yes.
Well. I guess I considered it and then said that, I didn't reference proposition 3.10. So I think really this should be collapsed into one proposition that references 3.10. But I think there's the other case that I mentioned but kind of dismissed without too much argument, which is, how do I know these segments actually intersect at all, right? What's to stop? I mean, obviously we can't draw it, but what's to stop like some wonky segment that goes around like this, and some, like, they just don't, none of them are contained in the other. Obviously, obviously you can draw it in 3 dimensions. But what's the argument for that? It would be pick a point. I'll pick a midpoint. And then, you have to be able to connect that. You can also connect that. And well, this is a kind of inside-outside thing, right? So is this point inside the green circle? If so, you can extend it, and it has to hit the green circle, and then you could argue that's that. If it's not inside the green circle, then it's outside, and since this point is inside, drawing a line from this point to a point outside the green circle has to meet the green circle.
Right.
So then if you take this midpoint, it's in both of them. So yeah, okay, I think that's satisfactory.
Yeah, I guess that's really the proposition you proved, right? Being able to draw the line so that it meets both of the circles. That right. This is maybe a more explicit way of constructing that. Whereas I think in the proof they just kind of say, well, you just draw this line and then it will meet both of them.
Yeah, I mean, I made use of I think we'd also have to buttress the notion of inside a little bit.
Right.
Yeah, I think this is unusually sloppy, this combination of propositions, right? Usually Euclid's pretty good at separating things. Yeah, all right, cool.